Hello everyone. So, welcome to the tutorial session about word vectors or word embeddings. So, we will see how we can use word embeddings to find out relation between words, or how we can find out again sentence representations or document representations using these word vectors. So, as you may be aware that we use the distributional semantic hypothesis, that is, a word can be defined by the words associated with it in its context. So, we use this notion to build up representations for word, and then we find similar words using this particular hypothesis. So, for this task what we will be doing is that we will be again using the same documents, the review documents that we have used in the previous tutorial. So, I have collected all of them together into a single CSV document here, and we use a data science library pandas that helps us in speedy processing of these, or more efficient processing of these documents. So, here we load all these documents into the data frame train. So, if we find train essentially has about 5387 documents, which are those documents which are like compilation of both positive and negative documents, and you were previously seeing those 5 samples from this document collection. So, as we were mentioning in the previous tutorial that a lot of pre-processing needs to be done before using this particular document set. For example, it has some extra HTML tags like br/, it has some other external markers. So, we will be removing them and we replace it with other normal characters. So, here this regular expression essentially looks for those entities which are in alphanumeric, and now what we do is that we will also do stop word removal. For this purpose we will be using the stop words that are stored inside NLTK. So, you can find NLTK corpus, we have imported the stop words. So, you might not have installed this by default in your system. So, what you can do is you can call the function NLTK download from the notebook itself. It will show a pop-up box where you can go and look for stop words package. So, you can just select on one of those packages, say stop words, and click on the download button. We already have it downloaded. Similarly, we will be using the tokenizer, which is the punct tokenizer, that also should be downloaded before this notebook has to be used. So, we take the stop words. So, I will be commenting it out, and we find these are the stop words. Once we have this, what we do is that we convert each review and we extract each individual word from those reviews. In that process we do the case folding and we remove the stop words and all other necessary pre-processing. So, we will be doing it for all of those sentences. Once we have it, we need to have a suitable vector representation or a list representation initially, and then convert it into a vector using the word embedding. Now, we will be using the word2vec embedding method. So, I assume you remember the word2vec embedding method that is taught in the class. Otherwise, I recommend you to go through the lectures and see how exactly word2vec functions. Unfortunately, we have gensim package that provides us the word2vec pre-implemented in Python. So, once we convert these sentences, we will be training the model. So, in Jupyter Notebook, you can use magic functions or magic keywords, where if you use something like time, it will tell how much time it requires to execute a particular function. So, from all the 5000 documents, we have extracted about 58,000 different sentences. So, we can have a look into how the sentence looks like. So, the first sentence looks like, this movie is a perfect example of an excellent book getting ruined by a movie. So, there are other reviews as well. Now, we have to convert each of these into a word vector. So, for each of this word, we have to get an efficient vectorial representation or a vector representation. So, what we do is that we have to set some parameters before we use this model. So, one thing is that we have to find how many or what is the dimension that the vector should have once word2vec learns the vectors. So, we expect it to be somewhere around 300. So, this is often set empirically after trying out various dimension sizes. So, your output vectors all for each word will be of size 300. Now, minimum words count. So, minimum words count is basically the number of times a word has to appear in the corpus to be considered for the vector formation. Maybe for this practical purpose, for this tutorial purpose, I will be keeping it a bit lower. So, this is a programming convenience, that what are the number of parallel threads to run. This makes your job faster, but it depends on the ability of your system. Next comes context window size. So, context window size essentially looks for, given a sentence, how many nearby words have to be considered. So, if I consider the word example, how many words left to the this given word and right to the given word should be considered while forming the vector for this word. So, as we know, distributional semantics depends on the word and its nearby context, and we here set a cap on the or a limit on the number of words that can appear in its context. Whatever appears beneath this count will be ignored by the model when we prepare the vector for each word. So, though we have about 58 sentences, in the interest of time, I will be using a less number of sentences here. So, we use the word2vec model. This word2vec model is defined in Gensim. So, we can see that from Gensim I am importing word2vec. So, once we have word2vec, we keep its size to be 300, which is num features, and we keep the min word count, the number of words that should appear, the number of times it should appear before appear in a corpus before it needs to be considered. So, so min count, ignore all those words with the total frequency lower than that particular count. So, you can use the shift tab keys in your keyboard to see the definition for each of these functions. Now, there is this parameter sg equal to 0. So, if you remember, there were two ways of using word2vec. One was the skipgram model and the other was the cbow model. So, when we keep sg equal to 0, cbow is used, but if we use sg equal to 1, the system will or the model will use skipgram model. So, here by default we are keeping sg equal to 0. So, we will train the model and let us see how much time it takes. So, in around 3 seconds we have our model trained. So, let us try to increase the count of sentences and see how much more time it takes. So, it takes almost double the size. So, there are some other arguments that you need to go through. For example, there we give a downsampling as the argument to the as the value to the argument sample. So, it essentially says that if you have a certain number of words that is much more than what we require, they are randomly downsampled. Similarly, here negative. So, when we use this function with this argument negative, it basically takes care of the negative sampling that Word2Vec efficiently uses. So, by default it looks for 5 negative samples. It can be set to varying values that will naturally affect the quality of the vectors that are generated. So, now what we do is that once we have the model where we have a vector for each of those words which are there in those 50,000 sentences, what we do is that we give a new sentence and see which of these words are most dissimilar to that in the model. So, we can find that kitchen is somehow not present in the word. So, it is ignored. So, amongst man, woman and child, so here child is the most dissimilar word from the other two words, that is man and woman. For example, let us see some other word, say let us take one of those words like perfect and see will this change the result. So, now amongst the 4 words man, woman, child and perfect, you find that perfect is the most dissimilar to the other 3. Now, we can also have this function most similar, which basically tells given a word what are the other similar words in the entire corpus. So, we can find the word man has other similar words which are woman, killer, father, etc., with its corresponding similarity score. The similarity score that typically used is cosine similarity, though other similarity functions can also be efficiently used. So, now if we find the word wife, the similar word that appears with a son, father, brother, girlfriend with its different similarity scores. So, though we cannot tell the exact relation between the words that is in the list, what we can find is that the words that appear similar to these words are in reality similar to the given word. So, if we give the word awful, we find other similar words that can be used in same context as the word awful can be used. We can find terrible, horrible, boring, dull, etc. So, this is essentially how we can use Word2Vec to find similar words. So, you can have a look into the Kaggle challenges where they have different competitions where we can use the word vectors. So, we have taken this tutorial from the Kaggle tutorial or the Kaggle competition called when a bag of word meets bag of popcorn, where you are supposed to build a task where you basically use the review data set to build word vectors and then use them for the sentiment analysis task that we have previously seen. So, they have different parts to this particular tutorial. It will be advisable to go through each of this. In addition, I will be just referring to the DogToA, which is an improvement over Word2Vec, or which is basically it cannot be said as an improvement, but it is a method to create vector representations for the document. So, we have seen in the topic modeling tutorial that we had representation, vector representation for each document. In this particular tutorial, we were not using any document representation, we were using a vector for each individual words. Now, how can we use this word2vec vectors to arrive at a document vector representation? And we have this DogToA method. So, you can look into the DogToA paper here, which is linked to this particular notebook. Here we will be using the default tutorial provided in GenSim. So, GenSim already has a corpus and it already has the DogToA implemented in its model. So, we can just import the corpus that is stored in GenSim, and we can find that they provide a tagged corpus. So, here is the corpus with individual words that forms the document and its corresponding tag is given. Similarly, there is another document with its tag given as 1. Now, we have a test corpus. So, in the test corpus the tag is not provided. Now, we instantiate the DogToA model. So, as in the word2vec, you can find different arguments that you can give to the DogToA. So, here size is the dimensionality of the feature vector. So, now each document will be represented as a vector with the given size, and you can look into other arguments as well. Now, once we have this model, we build the vocabulary and we use it to train the corpus. Now, with this model, when you have this vector that has the following words, only you can prevent forest fires, we get a representation for that particular document. We can see what is its size. So, we can find that the size of this particular vector is of 50. Now, once we have this vector for each of the document in our training corpus, what we do is that we take a particular document and we find its similarities with other vectors or other documents, and we then form a rank for each of them. Once we have this, once we have that computed, the similarity. So, what we have done is that we have taken the vectors for each different document and we have compared amongst themselves, and we find the similarity between those documents. So, what you find here is basically the similarity of a given document and its rank. So, lower the number, it is better, and we can find that a lot of them have very high similarity and they share the same value, hence are ranked at 1. So, let us see which are those documents. So, we were comparing this document and we find that the most similar and dissimilar documents are these documents. So, we can find the document 299 has the highest similarity, or one of those with the highest similarity is 83, and you can find, you can have a look into these two documents. So, essentially if you see, there are the contents in the both the document basically talks about very similar issues, and hence they have similar words in the context, and thereby the model is able to capture the document similarity. Here we find another document which is at the median. So, we can find that the similarity score between those at the highly ranked and the median are not much different, and still we can find the difference in the words that are used in context of all these documents, and the least similar document given here is this. So, all these documents are essentially coming from a single work or a single book, and these are different paragraphs of the same article. So, they are more or less similar, still they have a relative differences within their similarity. So, the DogToA essentially helps in handling the document similarity between documents in a given corpus. So, this is all that we will be discussing regarding distribution similarity or distribution semantics, especially using word vectors. Thank you.